The first talk in this session is by Ralph Neininger. Even though he's young, one could consider him a founding father of the contraction methods. He will tell us today, I'm gratified to be in this talk today because the contraction method is a very useful tool in the analysis of algorithms. And the less constraints and the less conditions we see and less assumptions, perhaps we can analyze more algorithms using it. So, Ralph, go ahead.
Yeah, thank you very much, Wassam, for the introduction. I will, at the end of the talk, I will show you a photo of the father of the method. And just in case that there's something you can wait for. I'm starting with a quotation from my session chair's PhD advisor, Boris Pitel. He had a paper in 1999 with the title Normal Convergence Problem, 2 moments and the recurrence may be the clue. And there he writes in the abstract or in the introduction the following sentences. For various global characteristics of large-sized combinatorial structures such as graphs, trees, one can usually estimate the mean and the variance and also obtain a recurrence with a structure size n serving as the recursive parameter. As a heuristic principle, based on our experience, we claim that such a characteristic is asymptotically normal if mean and variance are nearly linear in n. And I'm pretty sure most of you had experiences with limiting theorems where you had linear mean, near linear mean variance, and it was asymptotically normal. And we studied this sort of heuristic long ago with Uschendorf. And if you cannot recognize my voice and you also have the impression this guy on the screen is much older than Ralph, you may still recognize the slides here. This is a type of recurrence I've worked a lot on. And for the talk, you can just think of the yn of one-dimensional random variables, but you can also think of random vectors. And we consider a sequence which satisfies a recurrence of a quite general type. So you have the yn, and it should have the same distribution as the sum. So you have some coefficients, they are usually 1, but there could be some random matrix or some random factor in front. Then you have here some term I'm commenting in a moment about, and you have what in this community we often call a toll term. And so here we have coefficients, they are random matrices or random variables in the one-dimensional case. And we have the toll term, which is a d-dimensional random vector. And now here we have these indices, which are the sizes of the subproblems into which the original problem of size n is split. And there can be random, it can also be deterministic, they're just smaller than n, or n is also included for some cases, like tries, where sometimes everybody goes to one side and the subproblem has the same size with some probability. Okay. The 2 crucial conditions that we are usually using is that it's really a recurrence on the level of distributions. I call this here self-similarity condition, which means that these yr on the right-hand side, they have the same distribution as the yn on the left-hand side. So this implies, if you're in a specific problem, that your probabilistic model in the subproblems is preserved, that you really have the same distribution for the quantities and the subproblems. This is a self-similarity condition. And the second important condition that we're usually requiring is a sort of independence condition. And what's usually allowed is that you have dependence between these prefactors, the toll term, and the subproblem sizes. So I put them in one vector, and these components, they are allowed to be dependent, but the vector has to be jointly independent of these contributions from the subproblems. So these sequences which appear on the right-hand side, they need to be independent of themselves and also independent of this vector of all these coefficients. And in this setting, many theorems have been established and many applications have been given within the analysis of algorithms, a community, and also outside the AofA. Just to mention some typical applications, they include sorting and searching by divide and conquer algorithms like merge sort, quick select, or other bucket algorithms. Then search trees under natural probabilistic models like binary search tree, Emery search tree, quad tree, random recursive tree, and also digital structures for strings like tries, digital search tree, or Patricia, and many more. So there you find dozens and dozens, maybe hundreds of applications of such a setting. I think there's a microphone on somewhere. Okay, so what the talk today is about is that we will have to relax this independence condition, which I call conditional independence. Conditional because after you condition on the sizes of the subproblems, then the contributions of the subproblems become independent. And here you see in red the toll term. And in recent years, a couple of problems appeared where this toll term has not been independent as it has to be for this type of setting. So now I will relax this condition, but just dropping the Bn and only assume that the coefficients, the subproblem sizes, and the contributions from the subproblems are independent. And we'll develop a sort of general theorem in Boris-Pittel's sense for such a setting. To give you an example, which recently appeared from a paper of Diaconis and Kolesnik in the Advances of Applied Mathematics last year, they considered so-called Fibonacci matchings. This is the set of permutations where you're only allowed to map I. I is only allowed to be mapped to I minus 1, I, or I plus 1. No other images are allowed. And such permutations are considered, and you can visualize them as perfect matchings of bipartite graphs, where just these edges indicate the images of, if you put 1 to n on the left, you see the images on the right. And so this condition here for these Fibonacci matchings means that you can only map to the guy which is on your level, or you go 1 up or 1 down. There are no other connections allowed. And for example, if you have 4 elements, 1 to 4, then you will find 5 such Fibonacci matchings. The number Fibonacci matching comes from the fact that the size, cardinality of this set is given by the Fibonacci numbers, for the simple reason, if you can match 1 with 1, or you can match 1 with 2. If you match 1 with 1, you have still the number of matchings possible for the remaining n minus 1 guys, but if you match 1 with 2, you have to match 2 with 1, because otherwise you will violate this condition, and then you have n minus 2 elements left for the remaining matchings. So if you sum this up, you just get the Fibonacci recurrence, which gives you the Fibonacci number. Okay, but the study was about how to estimate this number. It was just a toy study. We know the number, but they want to estimate it by some important sampling algorithm. So they considered 3 algorithms to randomly generate such Fibonacci matching. And I will only show you one of them. The other 2 are somehow related. And the algorithm is described just by one sentence. In each case, in each step, sorry, you just match the smallest unmatched index, which has the maximal number of remaining choices. So what does it mean? For example, 1 has 2 possible choices. It can be matched to 1 or 2. But 2 has 3 choices. It can be matched to 1, 2, and 3. So everybody here has 2 choices until the last. This guy has only 2 choices. So the smallest index with maximal choices is 2. So, sorry. So you have these 3 choices, and then uniformly you choose one of them. Yeah. Okay. So you choose this one, but this enforces that the 1 is matched with 1. There's no other choice. Okay. Now you go on. Which is the remaining guy with the smallest index, but maximum number of choices is 4, because 3 has only 2 choices. You choose one randomly. And now in this case, 2 connections are forced. Otherwise, you will not be able to go on. And now the next step. So 7 is the guy with the smallest index maximal choices. And then you choose one at random and the other 2 are forced. Okay, this is the algorithm to generate such a random Fibonacci matching. And the quantity they're interested in is the probability under this algorithm. It's called AG. So here's the PG. G means greedy. You always take the guy with the maximum number of choices. So for this greedy matching algorithm, PG of pi is denotes the probability of pi to appear under this algorithm. And so in this example, it would just be, you need, in the first step, you have to do the right choice. Here you have to do the right choice in here. So it's independent choices. So you get 1/3 to the 3. And this would be the probability for this pi. Okay, and in the study, what they are interested in connection with this important sampling is, sorry, is the logarithm of this function pj applied to uniform permutation, because this quantity somehow can be used to measure the performance of the algorithm. So this is the quantity they study. And for this quantity, we will see that we have exactly the sort of recurrence I'm talking about, because here we have the product of the probabilities. So the logarithm just turns it into sum, and the minus just inverts the probabilities multiplicatively. And now how can we get a recurrence? One possibility is just we cut the problem at n½ yeah, and then we would say n½ has two possibilities. Either it has been chosen as one of these elements which really has a choice, then it contributes a factor of 1/3, which after inverting is a 3, and after taking logarithms, it gives a plus logarithm of 3. So this would be an additive Toll term, yes? And if it's a forced edge, which has been forced by other choices of other vertices, then of course it contributes essentially a factor of 1, which after logarithm it turns into 0. And then you can take the contribution of the top and the bottom part, and by taking logarithms, it turns into sum. And now the problem is that it's not so easy to preserve really the probabilistic model in the top and bottom part and to obtain this independence. And so they use some tricks by changing the quantity a little bit by a big O of 1, which asymptotic has no effect. So in 2 of their 3 algorithms, they managed to satisfy this stronger independence condition, which I first had, which I called conditional independence condition. But for this third algorithm, which I presented here, they found no way to really write it in a form or change it slightly to get here this independence condition. So they only could have this with dependence of Bn. Okay, in the paper for the first 2, they used some contraction framework from an older paper of Uschendorf and me, and for the third one, they then used some different method of some renewal argument, and then asked me if we can also do this. And since I had seen other such cases, I thought it's maybe we should have a general theorem for this, and that's what I'm talking here about. Okay, previous examples where we only had this relaxed conditional independence condition. The first one I saw was for so-called central limit analog of Quicksort. If you don't know what this means, I will discuss this later as an application of a general theorem. This was the first I saw, and then Noela Müller, who is probably here somewhere. And we studied some refined asymptotics of cyclic urns, and there this also appeared. And then Noela Müller in her dissertation also studied other urn models where similar problems occurred. And these 3 problems could also be solved by martingale methods, although I propose to use fixed point methods, and then just to be independent of this martingale framework, I propose to study another problem, which is the number of leaves in quadtrees, where you may know that there's also phase change for dimension 8. And for some refined asymptotic, Michael Fuchs, Noela Müller, and Henning Sulzbach, they also use the contraction setting to study this type of problem. I think this was presented at the AofA in Uppsala. Okay. Now, what is the principal problem with this relaxed conditional independence condition? Just recalling what we usually do. So Yn is our quantity. We do a renormalization. So we subtract something like the mean and divide by something like the standard deviation. And then we are writing down a recurrence for these normalized quantities, which looks like the original one, just the coefficients are new ones, which can be calculated. And this expression doesn't care, we can just calculate them. So then we have these normalized quantities for which we would like to prove a theorem, a limit theorem, so some distribution asymptotic. And So the first thing that we do, we check what the coefficients are doing. So we look at these coefficients in the equation on the right-hand side and try to identify jointly a limit. If there's no limit, we're in trouble, of course. But if there's a limit, then the idea is that this xn should converge to a random variable x in some sense, and this should be characterized in distribution if we just turn this equation to the limit. So if you go with n to the limit, we get x on the left and right hand side. We get here now the limits of the coefficients a, r, and b. And now the limit should appear also on the right-hand side, because we usually assume that these subproblems, they increase with n in some suitable sense. So on the right-hand side, we would get the axis independent copies and the coefficients. And now this is fine under this conditional independence condition, because then this vector here would be jointly independent of the xr. So the right-hand side is well defined. But if you only have this relaxed conditional independence condition, on the right-hand side, you may have dependence between b and the xr. And you would use this for general distributions. So it's not clear how to even define the right-hand side meaningfully. So this is the principal problem here. So now coming back to Boris-Pittel's heuristic principle. If we look at this principle from the perspective of the fixed point equation, well, Boris said that we should consider nearly linear variance. So typically this is n or n times some slowing varying function or some periodic function. And we assume situations where this subproblem size is essentially sum up to n, some minus big O of 1 or minus little of square root of n, so essentially to the original size. And now we look at the case where this b is 0. And whenever we encounter this case where b is 0, and in all the examples that I showed you, that I mentioned, I didn't show them, if you do the calculations, b will be 0. Then we have the following situation. If you just recall how these new coefficients a and r are calculated, these are just the standard deviations evaluated at the subproblem size divided, evaluated at the full size. And we assumed they converge to some limit. So now if you take the squares of them and sum them up, so the squares of the limits are essentially the squares of these guys. But if this is linear, it is just the subproblem size divided by n. But if the subproblem size is sum up essentially to n, this will be essentially 1. So we will face an equation where this b disappears, it's 0, and these prefactors, if we square them, they sum up to 1. And this is an equation which is fulfilled by the normal distribution. It's just the usual convolution property of the normal distribution. If you have a prefactor, it goes quadratic in the variance, and you have sums of independent normal, it stays normal, and the parameters add up. And with this condition, the variance stays preserved if you do the operation on the right-hand side. So this is from this perspective, the contraction method. This is the reason why this principle of Pittel really works, because we are led to situations where b is 0, and these guys here squared sum up to 1. And of course, if b is 0, we somehow also get rid of this additional dependence which we had in the problem.
Hey, Ralph,
okay.
AofA has a question now.
I have a quick question.
Yes.
If you remove b, 0 would be a solution. So what makes you preclude such a possibility? I mean, like, wouldn't be just normal?
Yeah, this is well observed. If b is 0, 0 is a solution. So if I here write 2 is solved by normal distributions, I also allow the variance to be 0 of the normal. Yeah, then it would be 0, a centered normal with a variance 0. So there's Dirac measure 0 is here considered to be normal distribution, but then later in the proofs, we will have to fix the variance. Yes, this is crucial. And if we fix the variance to be 1, we rule out this deterministic solution. So this is how on the technical side this is removed, this solution. But today I'm not going into details of the method. Okay, instead of going to the details, I'll present you some user-friendly theorem which you can apply if you have never read anything about the contraction method and don't want to read about the contraction method. So here you just need control in the moments and you get your normal distribution. So this is the recurrence I started with. I just put the prefactors to be 1. And I assume that they are all L3 integrable And now I only assume this relaxed conditional independence condition. So Bn can be dependent on these y's. And I assume that we have control in the expectation. So you have some expansion of the expectation up to some order. And also for the variance, you have some expansion. You need the first leading term, and the expectation you need up to a little of the order of the standard deviation as usual. And then you have to calculate these ratios, which usually you can easily derive these limits. And then you have to calculate this term here. Also in other methods, you will have to consider this term. And because we are in a case where b in the limit is 0, you have to show that they tend to 0 in L3. And if you have this, the only thing you need is to verify that these coefficients squared sum up to 1 almost surely, as we had on the previous slide. And then you have some minor conditions on the subproblem sizes, which are usually satisfied and easy to check, but a little bit messy to write down. So essentially saying that the subproblems grow with n. And if this is satisfied, you're done. Then if you normalize, you converge to the normal distribution. Okay, and so a similar theorem I had with Ruschendorf, and this has been applied several times in the last 20 years, but that was under this stronger condition where you have independence of the Toll function. So now we can do it also without this independence. Then in the extended abstract of the conference, there's also a multivariate version. Here I'm in talk, I only discuss one-dimensional settings. So there you can look up a multivariate setting. The proof uses a Solotaryov metric. As long as you're only interested in V convergence, you don't have to know anything about the metric in use. And the proof can also be quantified. So in the extended abstract, and also here I briefly discuss also a bound on the rate of convergence, but only in this theta 3 metric, which I will comment a bit about later. And the last comment is the main work, if you want to get this normal convergence, is not this theorem. The main work often is to get an expansion of the variance, or even the mean may be difficult. So here it's like Svante Janssen on Monday said that we should be interested in many techniques and using many different techniques to be able to solve a problem. So here, just with this theorem, you may be able to do simple cases or cases where you are lucky with the moments, but in other cases, the major problem may be in these expansions of the moments. Okay, just a comment on the rate of convergence. So we will have, what we need is that these guys converge to limits, and the limits squared sum up to 1. So this sum here would have to converge to 1. And now if you know how fast it converges, and here we need a L3½ norm raised to the power 3/2. And this Toll term has to tend to 0. This is after normalization. So if you know how fast this tends to 0, then you can just check how fast these coefficients converge. Say this is a big O of some function R of n, and R of n tends to 0. And it cannot go too fast to 0. There's a technical condition. You can this somehow restricts the speed. If R is too slow, if R is too fast, this ratio is becoming too large, and then this will no longer be satisfied. So there's a certain natural bound on the speed which you can have by our theorem. And if you have this, then you get this normal convergence, excuse me, with a rate of convergence. So this R of n you can also have as a rate in this Solotaryov metric theta 3, which I did not define. So this metric is strong enough to imply V convergence. So this is used in the proof. But it's not so popular for estimating rates of convergence because you cannot easily switch to more standard metrics like the Kolmogorov-Smirnov. You can switch in such cases, but you usually lose in the exponent, which people then are no longer interested in. But at least we can have also the rate of convergence. But what I regret here is that this is the condition with this relaxed conditional independence condition. So if you have dependence, if you have the stronger conditions, so where we have independence with the Toll function, then here we would have an additional exponent 3 at this Bn. This 3 norm would be raised to the power 3, which makes the rate much faster. So this may be a limitation by our techniques or by our abilities, but I just don't know if this is in some sense tight or if we are missing here something. Okay, the extended abstract also has a multivariate version for the rate of convergence if you want to check it. Okay, so now I have two applications. One is the central limit analog for quicksort. Just recalling quickly, we consider the number of key comparisons of quicksort, say on a random permutation or some uniform sample, or you can also take the pivot uniformly. I denote this by Kn, but now you cannot really do what I say. I assume an embedded version as the path length of a binary search tree, which is growing almost surely. So on a joint probability space, you can have this with quicksort if you always take the first of the pivot element and generate your sequence as IID uniforms. So one can achieve this, but one can also have situations where this is not embedded. Okay, and then Renier showed long ago that you can normalize this to martingale, which is L2 bounded, and you get almost sure convergence by martingale convergence to a limit Q. And then there are different directions where this has been refined. One interesting one is in a paper by Benjamin and Phil, which was presented, I think, on the AofA meeting in Montreal, where they were able to, so this is in a joint probability space, if it's almost surely, so you can subtract them, and they were able actually to get an explicit formula for this L2 distance, and which is asymptotically 2 log n over n. And this Q, this limit here, it has to be, then one has to use this fixed point equation of Uwe-Rösler, which is just in distribution. And they had, by some almost sure construction, had also to give sense to this equation on a joint probability space almost surely. So this was this L2 distance. And then I was able to just renormalize this martingale residue, blowing it up appropriately according to this order here, and then this converges to the normal distribution. And now all this can be written in recurrences. You have a recurrence for quicksort given by the algorithm, and these sort of quantities then have recurrences. But if you write everything out, you will see that this toll function then will be dependent on the quantities itself. So you won't have these general conditional independence conditions. You only have this relaxed condition way of dependence. But this is perfectly covered by our theorem. And so we also get a rate of convergence, which here in theta 3 is 1 over square root of log n. And due to this exponent 3, which I discussed on the previous slide, I'm actually not sure if this is the correct rate. It might be log n to the -3/2, because I studied another example, which is a little bit different, but related. And there I was able to improve from -1/2 to -3/2. So for this reason, I'm not so sure about this rate, but okay, this is what we have. Okay, so what I did not show you now is this fixed point equation for Q. And I don't longer have to write it down because Uwe-Rösler, he now has it printed on his suspenders. And here's the picture. And here you see Uwe-Rösler, he is the father of the contraction method. And you may see here on these suspenders, there's something written here. No? I don't know if you can see it in Philadelphia. If not, I will zoom in. So here you see something. Now I rotate Uwe by 90 degrees. So Uwe is now in the air, and here is it. So here you have the fixed point equation for quicksort on Uwe suspenders. Okay, so another example coming back to these Fibonacci matchings. There we had a similar equation. I didn't specify precisely how these quantities look like, and the Bn also not precisely, but you have to believe me that the version they have in the paper is with dependence of Bn. And so also this cuts there that they have no way to make it independent by some small change, but it is perfectly fine for our setting. So if you look at this logarithm of this probability on a uniform sample, then Diaconis and Kolesnik, they showed that the expectation and variance are linear, as in Pittel's heuristic principle, and calculated also these constants. And then by some unique argument, they had these normal convergence theorem. And the theorem you can apply, you can calculate everything and work out the rates as well. And so you can just automatically get the normal distribution here. And the rate of convergence that we get for theta 3 is n to the minus 1/2, unfortunately, plus epsilon for any epsilon. But there is some epsilon, which is in some examples, we can get rid of these epsilons, but in some examples, I think we are technically just too weak to get rid of the epsilons. Okay, so that's it. Thanks for your attention. And yeah, I'm interested if you have questions.
Jim still has a question.
Okay.
Yes, I have a short question and a meatier question. So the first question is for the example you showed where you said you can get log n to the minus 1/2 convergence rate, and you think maybe the true story is log n to the minus 3/2. Do you have arguments to say it's not better than log n to the minus 3/2?
No, I have no arguments. The only way I know to do this would be an expansion of the third moment. And this is maybe painful. Yeah.
My other question that has more substance to it is, so this was all about the Pittel world, about the normal world. So suppose we do classical quicksort, for example, as an example of another family of problems. Now the question is there any hope in those sorts of problems of being able to relax the CIC condition to RCIC?
Yes, I see one way to do this, and this should work. So, you know, here in our example, it just tends to 0, so we automatically get rid of the depends. So if you can write it as an independent part plus some small dependent part, then you would get general limit equations. So you could probably get a full theory of all sorts of distributions with as long as this dependence is small asymptotically. So I think this is just one example of such a theorem where this tends to 0, but if you tend to something which then is independent in the limit, it should be fine, I think.
Right,
But
and if you go beyond that, the sort of...
Then I don't know how, as I said, then I don't know how to define this right-hand side.
Yeah.
This is a major problem then. Yeah, we just did the obvious thing.
Right, thanks, Ralph.
Any other questions?
There's nobody else on.
I have a quick question, Ralph.
Yes.
Your Qn theorem, Qn minus Q, can you get to that?
Which one? The
Qn minus Q.
The quicksort residual.
Yeah.
This is strikes me as a strange result. Are you saying that Qn minus an unknown distribution, it converges to a known distribution?
Not exactly. I'm saying that everything can be embedded in one probability space. This is part of the paper of Jim Phillips, and then you have the Qn and the Q. You have an adjoint probability space with almost sure convergence. So the difference tends to 0 almost surely. Yeah, this is.
I understand, but nothing much is known about Q itself, right?
This is right. Yeah, well, you have a series representation. You have a sort of complicated series representation, which this guy sort of resembles for large n. But what I say is you can blow this up, and you get a well-known distribution, which at the first moment was sort of a surprise, but then later we understood that this is sort of often the case for martingales, that you can blow up the residual and you get a normal, or you get a mixture of normals in other cases where the variance is random, some mixture for random variance, like in multi supercritical branching processes. You have these sort of theorems that they were developed in the 70s by I forgot the names. Some Australian guy did these sort of theorems.
Okay, we thank the speaker again. Is there other anything?